Hello everyone. Today we're going to look at what is a graph and what is a digraph, or any mathematical object involving points and connections between them may be called a graph. As we can see on the left hand side, this is a graph. If all the connections are unidirectional, it is called a digraph, which is on the right hand side, as you can see with these arrows between the vertices. Okay. Here's some definitions. A graph G equals VE consists of two sets, V and E. The element V are called vertices. As you can see, I'm pointing to number 6. That is a vertice. The elements of E are called edges. As you can see over here, I point to the edge between 4 and 3. Each edge has a set of 1 or 2 vertices associated to it, which are called its endpoints. An endpoint is said to join its endpoint. An edge is said to join its endpoints. For example, this edge over here has endpoints 4 and 6. All right? The subscripted notations VG and EG, or VG and EG, are used for the vertex and edge sets when G is not the only graph under consideration. This makes sense if you have two graphs, one F and one G. Just saying the set V, it's not clear whether it belongs to F or whether it belongs to G. So you need to differentiate by saying VG or VG like that. Okay. If vertex V is an endpoint of edge E, then V is said to be incident on E, and E is incident on V. As you can see down here, we have edge E between 4 and 6. And this is between, well, we label those vertices V. And this means that V is incident on this edge E. And this edge E is also incident on vertices V. This will be a bit more prevalent when we look at directional graphs, because of course this incident into 4 is very different from an edge going out of 4. All right, so just take note of this right now, but it will become more relevant later on. A vertex U is adjacent to vertex V if they are joined by an edge. As you can see over here, 6 is adjacent to 4, and vice versa, 4 is adjacent to 6. Okay, they are joined by one edge. So all of the vertices adjacent to 4 is going to be 6, 3, and 5 respectively. Two adjacent vertices may be called neighbors. As you can see again, 6 and 4 are neighbors. And if we look at, let's say, 5, all of 5's neighbors are 4, 2, and 1. Okay. Adjacent edges are two edges that have an endpoint in common. If we look at the vertice 4, an adjacent edge would be the edge going from 4 to 6, another one would be 4 to 5, and another one would be 4 to 3. These are all adjacent edges because they all have the common endpoint of 4. Makes sense? All right. A proper edge is an edge that joins two distinct vertices. This will make a lot more sense with the edge coloring, so we won't go into this too much right now. And edge coloring just means that adjacent edges cannot be colored the same color. That would lead to a proper edge. So yeah, we won't speak too much about this now. Just know that a proper edge exists and it joins two distinct vertices. A multi-edge is a collection of two or more edges having identical endpoints. For example, this edge and this edge both share these two endpoints. Therefore, this is a multi-edge, as we denote over there. A simple adjacency between two vertices occurs when there is exactly one edge between them. For example, between 6 and 4, we have a simple adjacency. If we add another edge over here, there's no longer exactly one edge between them, so it is not a simple adjacency anymore. The edge multiplicity between a pair of vertices, u and v, is the number of edges between them. Pretty straightforward. Here we have one edge, here we have two edge. If we add another edge, we'll have three edge, and so on. Okay, this makes sense. A self-loop, or just a loop, is an edge that joins a single endpoint to itself, as can be seen over here. All right. And now if you remember the incident scenario where you count the number of edge incident to a vertice, I hope you are thinking about that when you see the self loop. You will notice that this is a bit of a strange scenario because an edge is going out and then it's coming back in. So how does this affect the incidence? Well, we're going to get into that into another video. For now, this is not so important. Let's go over an example, putting everything together. A line drawing of a graph G with V and E is shown in this figure. It has a vertex set UVWX, okay, UVWX, and edge set A, B, C, D, E, F, A, B, C, D, E, and F. The set AB, okay, these two edges, is a multi-edge with endpoints U and V. That is correct. Yes, they share the same endpoints. And edge C is a self-loop, as we can see over here. Great. A simple graph is a graph that has no self-loops or multi-edges. It's simple, right? It looks just like this. A trivial graph is a graph consisting of one vertex and no edges. Great. And a null graph is a graph whose vertex and edge sets are empty. Obviously, I cannot draw this because there's nothing there, right? An edge joining vertices U and V of a graph may be denoted by the juxtaposition UV. If it is the only such edge, occasionally the ordered pair UV is used in this situation instead of UV to avoid ambiguities when multi-edges exist, or whenever else desired, the edges of a general graph may be given their own names. Okay, so there's a lot of rambling, just saying that whenever you denote an edge from, let's say, vertex A to vertex B, it is common to write either A, B, or in the case of ordered pairs, if this was directional, where the direction mattered, you could write A, B like this, okay? Because obviously you can go from A to B in this case, but you cannot go from B to A. If this was bidirectional, like a normal graph, then this order wouldn't matter and it would be equivalent to B, A. Okay, that's all this is saying. And the simple graph shown here has edge set UV, okay, VW, VX, and WX, as we can see. The order that you display these does not matter. Whether you want to say WX first, then VX, whatever, it doesn't matter, okay? Many applications require non-simple graphs as models. Moreover, some non-simple graphs serve an essential role in theoretical constructions, especially in constructing graph drawing simple and non-simple on surfaces, which we'll see in Chapter 7. Although the term graph means that self-loops and multi-edges are allowed, sometimes for emphasis the term general graph is used. Okay, so a rundown: simple graphs means no self-loops and no multi-edges. General graph means there is self-loops and multi-edges allowed. And if people just use the term graph, they're probably referring to general graphs because they are more widely used. A loopless graph is a graph that has no self-loops. It might have multi-edges. Sometimes a loopless graph is referred to as a multigraph. Okay, as you can see over here, there's a multigraph. Now this means that general graph has has loops and has self-loops and also has multigraphs inside of it. This means that multigraphs, but down below, have multi-edges but no self-loops. And of course, simple graphs, sorry, I should have drawn this. Simple graphs have no self-loops and no multi-edges. So it goes general, allows both self-loops and multi-edges. Then multigraph allows just multi-edges, and then simple, it disallows both self-loops and multi-edges. Okay. A dipole over here is a loopless graph with two vertices and n edges between them. In this case, we have D2 because there's two vertices and the n edges is 2 in this case. If we add another one, it will be D3. Okay. A bouquet, which yes, it does look like a flower, B of n, is a graph with one vertex and n self-loops. In this case, we have B of 3. Makes sense. The loopless graph in this figure depicts the benzene molecule C6H6. And this shows you a little bit of how we can model chemistry as graph theory, where these edges between vertices indicate a bond between vertices. All right, very cool. The dipole D3 is shown. Yes, there it is. This is a D3 graph. Two graphs with self-loops are shown. As you can see over here, we have two vertices with self-loops, and they call it the dumbbell graph. And over here is a bouquet B4. Allowing graphs to have additional attributes beyond vertices and edges enables them to serve as mathematical models for a wide variety of applications. Two of the most common additional edge attributes, both described in great detail later, are edge direction, which we've already spoken about, and edge weight. Another common attribute is color. Graph coloring is discussed in chapter 5. Okay, so this is just saying that a graph with just random vertices and edges doesn't really mean all that much. But once you start adding direction into it, it now has a bit more meaning for real life applications. And you can also associate weights to these edges that could indicate time, efforts, cost, whatever you can think of really. With that, you can also add labeling, which could be useful. And then also you can associate colors, which again groups a graph into more separate buckets, if we per se. So this just says that a real life model of a graph will be very different to what we've gone through so far, where it will have direction, weight, color, all these things that give it meaning. A vertex attribute is a function from the vertex set to some set of possible attribute values. For example, over here, you could see we apply some function, and now our vertices have labels. Great, that's all that means. An edge attribute is a function from the edge set to some set of possible attribute values. Again, for example, here we put some function, and our edges now have some, value that could mean whatever. In this case, it's a waiting for, let's say, time. Okay. A digraph is an edge between two vertices, creates a connection in two opposite senses at once. Assigning a direction makes one of these senses forward and the other backward. Viewing direction as an edge attribute is partly motivated by its impact on computer implementations of graph algorithms. Moreover, from a mathematical perspective regarding directed graphs as augmented graphs, makes it easier to view certain results that tend to be established separately for graphs and for digraphs as a single result that applies to both. The attribute of edge direction is developed extensively in chapter 3 and elsewhere. Great. We don't have to go into any of this right now. All we know is an edge can have direction. From this case, you can only go from 4 to 0. You cannot go from 0 to 4, as there's no direction going there. Of course, you might notice you can go from 3 and then to 4, but that's not what I mean. I mean a direct edge leading between those two. A directed edge or arc is an edge E. Okay, here's E. One of whose endpoints is designated as the tail. There's a tail. And whose other endpoint is the head, right over there. They're denoted head E and tail E respectively. As you can see, the tail is, the endpoint of the arrow, and the head is where the arrow is going to. Okay, that's how you denote that. Directed edge is said to be directed from its tail and directed to its head, which we just spoke about. The tail and the head of a directed self-loop are the same vertex. That's something to note, okay? A multi-arc is a set of two or more arcs having the same tail and head, as seen over here. This means that a graph like this is not a multi-arc because the tail and head are not the same vertex for these two edges. Sorry, arcs in this case. A digraph or directed graph is a graph each of whose edge is directed. Makes sense. A simple digraph is a digraph with no self-loops and no multi-arcs. As seen over here, this over here is not a simple digraph. A mixed graph or partially directed graph is a graph that has both what am I saying? A mixed graph is a graph that has both undirected and directed edges. In a mixed graph, using the unmodified term edge avoids specifying whether the edge is directed or undirected. They just mean that if you refer to an edge of this graph, it's ambiguous whether you are referring to this directed edge or these undirected edge. Okay? The underlying graph of a directed or partially directed graph G is the graph that results from removing all the designations of head and tail from the directed edge of G, i.e. deleting all edge directions. As we can see from here, we get this. This is pretty self-explanatory. Notation. In a simple digraph, an arc from vertex U to V is commonly denoted UV. As from the previous graphs, it's very much the same. When multi-arcs are possible, using distinct names is often necessary. However, in a directed graph, these ordered pairs actually have meaning. So if we have U and V, our ordered pair of U and V has meaning because this means we go from U to V, and this is not the same as saying V to U because this doesn't exist in our graph. It's one directional. And they're saying that if you have multi-arcs like this, just saying UV is not very clear. You should probably label these edges something else. Okay. The digraph on the left has undirected graph, on the right is underlying graph. The graph has two multi-arcs, A and B, as we can see over here, and F and H. F and H. There we go. Right, and that makes sense. You can look at it, confirm it. There's the underlying graph. Everything makes sense over here. A simple digraph can have one arc in each direction between two vertices as illustrated over here. A simple digraph whose underlying graph is not simple. This is very important. As you can see over here, this is a simple digraph, but its underlying graph will be over here, which is not simple because it contains a multi-edge. Very important, even though this is not a multi-arc. When vertex set of a graph is partitioned, the cells of the partition are commonly assigned distinct colors. This is developed at length in chapter 5. You don't have to worry about it now. Just know that this is possible. You can partition the set of vertices and color them. A vertex coloring of a graph G is a function from its vertex set VG vertices to a set C whose elements are called colors. As you can see over here, I have written out the vertex set of G, and you can sort of partition them into colors. For example, here, let's say I've partitioned R1 into the red coloring, R2 into the red coloring, R3 and R4. Okay, but these other vertices will have a different set of coloring. There will be blue over here, and they will map to that instead. A vertex coloring is proper if two adjacent vertices are always assigned different colors. For example, over here, if this one was blue, like this one, it would not be a proper coloring. A graph is C colorable if it has a proper vertex coloring with C or fewer colors. For example, over here, we have a 3 coloring. Okay. Great. The vertex chromatic number of a graph G, denoted as chi, the Greek letter, is the smallest number C of colors such that G is C colorable. Okay, so it's the least amount of colors required. For example, this is 3, but it can also be 4 colorable if I just make this color green, for example, right over here. Then it would be 4 colorable, but that's not its chromatic number. The chromatic number is the least amount of colors required to color in the graph, which in this case is 3. Definitions of edge coloring: C edge colorable and edge chromatic number denoted by the that little sign. G are obtained by simply replacing the word vertices with the word edges in the definitions above. Okay. So that just means that everything we covered previously can be replaced with edge instead of vertice, and these all still apply. The graph G in figure 1.1 is shown with 3 coloring of its vertex set. Since there is not 2 colorable, its chromatic number is 3. Also, the graph is easily seen to be 3 edge colorable and clearly is not 2 edge colorable since chi prime G is 3. Okay, great. As you can see here, you can check for yourself that this can only be colored with 3 colors, and similarly the edge is also 3 colorable. Okay, and you can confirm this yourself. And a graph G and they're just saying this graph G has the same chromatic number for edge and vertex coloring. We'll go into later about these type of cycle type shapes and how this can be generalized more for the coloring and the edge coloring. And right now, since this is the first episode, we have some useful things of graph theory. You know, why are we even doing graph theory in the first place? Well, here's some useful areas where it can be applied. In computer science, networking algorithms, and data structures, graph theory is foundational for designing and analyzing network systems, developing algorithms, and structuring data in computer science. For instance, networking relies heavily on graph theory to model and manage connections between devices. Namely, network topologies are represented as graphs to optimize data transmission and routing. Algorithms such as Dijkstra's and Kruskals are employed to solve shortest path and minimum spanning tree problems, respectively. Additionally, graph theory underpins data structures like adjacency lists and matrices, which are essential for efficient data manipulation and retrieval. In biology, it models biological networks. Graph theory is also instrumental in biology. It's used for modeling and analyzing complex biological networks such as protein-protein interaction networks, metabolic pathways, gene regulatory networks. These networks are represented as graphs where vertices denote biological entities, example proteins and genes, and edges represent interactions or relationships between them. This approach helps researchers understand the intricate relationships within biological systems, predict functional outcomes, and identify potential targets for drug development. Social sciences, social network analysis. In social sciences, graph theory is used to analyze social networks where individuals are represented as vertices and the interactions or relationships are depicted as edges. This analysis helps in understanding social structures, influence patterns, and community dynamics. Applying concepts such as centrality and connectivity enables researchers to identify key influences, study the spread of information, and analyze social behaviors. We also have transportation for traffic flow and urban planning. Most people don't know this, but roads, intersections, and transit routes are modeled as graphs to optimize traffic flow, reduce congestion, improve route planning. Graph-based algorithms help in designing efficient transportation networks, managing public transit systems, and planning urban infrastructure. Analyzing these networks help planners make informed decisions to enhance mobility and connectivity within cities. That's the end of this episode. Thank you for watching. If you liked, please like the video and subscribe. Comment down below if you have any questions. And this is the first part of a playlist, which we will hopefully go through all the aspects of graph theory in fullest. Thank you.